Welcome students to Unit 11, Lesson 2, Right Triangle Trigonometry. This video will not be for the entire lesson. I'm going to teach part of it in our next block, but instead of being in note held, most of the first part of this is review, and that will allow us to have more time in the block to do some work. So by the end of this lesson, not necessarily this video, you need to be able to evaluate trigonometric functions of acute angles, and the part that I'm going to teach in class has to do with this fundamental trigonometric identity stuff. All right, so let's talk about a right triangle. It is a right triangle, if you remember from geometry, because we have a right angle in the bottom corner here, denoted by a box. And the other two angles have to be acute, because as hopefully you recall from geometry, the sum of the three angles of a triangle have to equal 180. And so if we've already pulled out 90 from it, we have 90 degrees left over to divvy up between two angles. So they have to be less than 90, therefore they're acute. Oftentimes we denote an acute angle by the Greek letter theta. And if you don't like the Greek letter theta, which I usually write like as a circle with like a line that kind of comes through the middle, you can use X, you can use Y. Just oftentimes angles are denoted by Greek letters. All right, so if you're wondering, why do we need this theta stuff? Well, in order to talk about one of the acute angles, since there are two, we're going to put theta in this angle, and for now we're just going to talk about that acute angle. And we are going to describe we're going to describe all of the sides of the triangle, the right triangle, in relationship to that angle. So, for instance, this side of the triangle. That side of the triangle is opposite the 90-degree angle. Therefore, that's the hypotenuse. And that's true in a right triangle. The longest side, the slanted side, the side opposite the 90-degree angle is hypotenuse. But then the other side are legs. And we need to talk about, well, how do we talk about which leg is which? One is adjacent and one is opposite. The side that does not touch theta is considered my opposite side. The side that does touch theta is considered the adjacent side. So if we had written this triangle and I had put theta up top, this would be the opposite leg, this would be the adjacent leg. However, this would still remain the hypotenuse. Always remember the power of pause, stop, and rewind. So I'm not going to give a lot of wait time between explanations. All right, so let's talk first about what's above the blue line, ratio. A ratio of right triangles' three sides are used to define 6 trigonometric functions. But if we think about what a ratio is, all a ratio is a comparison of two items. If you were bored out of your gourd and you went to Deerberg's and you counted all the oranges and all the apples, and there were 320 apples and there were 120 oranges, then that would be your ratio of apples to oranges. If we wanted to count, and let's say that we had 7 boys in the class and we had 12 girls in the class, then we could say it was 7 to 12. You could write it 7 to 12, or I could write it in a fraction form. And this is how we tend to write our trigonometric ratios. Then we give them names. So if I wanted to, I could call this the Knopp ratio. The Knopp ratio would be defined as the ratio of boys to girls in the class. I can give it any name I want. I could give it, BG. I could call it the trig ratio BG, but we just give it a name. So in trigonometry, we give the following names to the sides of a right triangle. We give the sine as the opposite leg over the hypotenuse. And you have to define the theta. So you cannot have a flailing sine. This is incorrect. It is incorrect to write the sine equals 6 over 7. How do I know what angle you're talking about? So that is an incorrect statement. You must always take a trig ratio of an acute angle in that right triangle. So that theta is necessary. Another ratio called the cosine ratio is a comparison of the adjacent over hypotenuse sides of any right triangle. And the tangent, which is abbreviated as tan, is the opposite over adjacent, or the opposite leg over the adjacent leg in any right triangle. How do you remember this? Most of you probably learned SOH-CAH-TOA, or if you're from St. Louis, SOH-CAH-TOA. You know, people from Boston, they park their car and have a yard. Well, you need to make sure you spell SOH-CAH-TOA, very St. Louisan. We eat our park with a fark on how we farty far. So make sure when you spell it, it's SOH-CAH-TOA. And this is just a mnemonic to kind of remember that the sine is equivalent to the opposite over hypotenuse. That's the ratio. The cosine ratio is the adjacent leg over the hypotenuse. And the tangent is opposite over adjacent. Now, these are not the only trig functions that we have. All right? We also have reciprocals. So in my opinion, if you stopped me in the hall, I don't know that off the top of my head, I could tell you that the cosecant, which is abbreviated by CSC, is hypotenuse over opposite. I don't know that I could tell you the secant, which is denoted as SPC, is the hypotenuse over adjacent. I don't know that I could tell you the cotangent is the adjacent over the opposite, but this is what I can do. I can tell you that the cosecant is the reciprocal of the sine ratio. Those are reciprocals. You need to think of them as buddies. They're a pair. The secant is the reciprocal of the cosine. And the cotangent, and this is kind of the only one that makes sense, is the reciprocal of the tangent. This is what I remember. So going back to SOH-CAH-TOA, okay, if I go back to SOH-CAH-TOA, here is honestly what I remember. If you ask me about the cosecant, I have to remember that the sine is the reciprocal of the cosecant. And if the sine is opposite over hypotenuse, then the cosecant is hypotenuse over opposite. That's the thought process I go through. If you are asking me about the secant is the reciprocal of the cosine. If the cosine is adjacent over hypotenuse, then the secant is hypotenuse over adjacent. It's just the reciprocal. It's just flipped. And if I want to talk about the cotangent, then the cotangent is the reciprocal of the tangent. And how do I remember their pairs? Tangent and cotangent make sense. But you have to remember that the sine family is reciprocals to the secant family. And one gets a co and one doesn't. So sine and cosecant are reciprocals. Notice how there's a co on the secant, there's no co on the sine. Cosine is reciprocals with someone in the secant family, and since cosine has a co in it, it's reciprocal with somebody that doesn't. All right, so let's use this information to try an example. We need to evaluate the 6 trigonometric functions of the given angle theta, and I want this in simplest radical form. No decimals. So let's look at angle theta in the problem. Okay. If I look at 10 is going to be an opposite side or an opposite leg of angle theta. 5 is going to be adjacent, and the hypotenuse is unknown. But I know a handy-dandy little theorem called the Pythagorean theorem, which can be applied to any right triangle if you know 2 sides and are trying to find the third side. So I'm going to set this up as 5 squared plus 10 squared equals c squared. And that's 25 plus 100. And as a reminder, I want simplest radical form. So when I take the square root, you technically get a plus or minus, but we're talking about distance. So it's unnecessary to really look at the negative. So 125 is 25 times 5. So c is equal to 5 root 5. Now, you don't have to organize your work like I do, but this is my thought process. I need to find the sine of angle theta, I need to find the cosine, and I need to find the tangent. And what I do directly opposite them is write the reciprocals. So the reciprocal of sine is the cosecant, the reciprocal of the cosine is secant, and the reciprocal of the tangent is the cotangent. All right, friends, now we're going to use SOH-CAH-TOA. So the sine is the opposite, which is 10, over the hypotenuse, which is 5 root 5. I am going to simplify this because I can't have a radical in the bottom, but I'm going to give you a tip. Wait until the end and hold on for about 30 seconds and you'll see why. The cosine is adjacent over hypotenuse, so that's going to be 5 over 5 root 5. And yes, I'm going to have to simplify. And my tangent is the opposite, which is 10 over 5. Now, I encourage you now to flip. The cosecant is just going to be 5 root 5 over 10, which is the reciprocal of sine. The reciprocal of cosine is 5 root 5 over 5. And the reciprocal of the tangent is 5 over 10. The reason I feel like it's helpful to flip now instead of at the end is because notice how these values no longer have to be rationalized. If you rationalize this first, so I get 2 over root 5, and then I would rationalize, my final simplified answer for the sine of theta is 2 root 5 over 5. If you would flip it now, then you would have 5 over 2 root 5, and you end up having to rationalize all over again and simplify, when honestly I could just reduce the 5/10 and I get root 5 over 2, and in my opinion it reduces your workload. All right, so same here. This is 1 over root 5, and when I rationalize, I get root 5 over 5. Over here, the 5's cancel, and I get root 5. I don't have to spend my time flipping and re-rationalizing. And then 10 over 5 is 2, and then 5 over 10 is 1/2. So we didn't know exactly what the angle was, but we knew what the ratios of those opposite over hypotenuse, adjacents and hypotenuse, opposites and adjacents were in this right triangle. Example 2 is very similar to example 1. I just didn't draw the triangle, and I didn't mark the triangle for you. So for those of you that are visual, this is the beauty of this. Some of you don't need a picture at all. Some of you need that picture. So let me draw a right triangle. All right. This is my right angle. It is up to you where you want theta. I'm just going to write theta in the bottom right corner, but honestly, you could have written it in the top. Now, here's my thought process. So this is what's not thinking. You might not have to write this when you actually do your homework, but here's what's going through my mind. They gave me information about cosecant. That's the reciprocal of sine. Sine is defined as the opposite over hypotenuse ratio. That means cosecant has to be the hypotenuse over opposite. So 10 has to be by hypotenuse, and opposite of theta is 7. And now this problem hopefully looks to you exactly like example 1 did before we found all of the information. So in this next problem, I do have to find the adjacent side. Because the 6 pieces of information, I have to find the sine of theta, which I don't need the triangle for. It's just the reciprocal. So I know this piece of information without really doing any work. But in order for me to find the cosine or the tangent, both of them require an adjacent side. Therefore, their reciprocals also require an adjacent side. So I'm going to have to do, and as you guessed it, Pythagorean theorem to find this side of the triangle. So I have 7 squared plus b squared equals 10 squared. Again, I want simplest radical form. So b squared is going to be 100 minus 49. So b squared is equal to 51. And when I take the square root, root 51 cannot be simplified. So root 51, while irrational, is the length of that side of the right triangle. So when I go back to fill this in, remember cosine is adjacent over hypotenuse. So that's going to be root 51 over 10. Tangent is opposite over adjacent. So that's going to be 7 over root 51. I get their respective secant and cotangents by taking their reciprocals. So I think it's a lot easier to think of them as reciprocals than trying to go through their definitions. And now when I look, I need to simplify 10 over root 51 and 7 over root 51 by rationalizing. So when I rationalize, the tangent is 7 root 51 over 51, kind of ugly, but it's not awful to deal with. And my secant is going to be 10 root 51 over 51. If 10 over 51 or 7 over 51 could reduce, you should do it, but in this case, they do not. All right, we have 2 more slides, and then I will pick up the rest of the lesson during our block. But we need to talk about evaluating trig functions of a 45-degree, 45-90 triangle. All right, notice how I don't have any lengths on here. And I would argue that it doesn't matter, because if this is an isosceles right triangle, right, this means my legs have to be the same by definition of an isosceles triangle. If my base angles are the same, that means the angles opposite them are the same. I know, it's a geometry flashback, get over it. So if these are the same, all right, I'm just going to give them the number 1. All right, and in just a moment, give me some time. I'll assign a different number so that you can see that whatever number I picked was just relative. All right, you might remember what the hypotenuse is from special right triangles, but if you don't, isn't 1 squared plus 1 squared have to be my hypotenuse squared? So 1 plus 1 is 2. So this means that my hypotenuse is root 2. So you might remember those ratios from your special right triangles. So now let me erase all of this garbage and make this clear that this is 1, this is 1, this is root 2. It makes no difference which 45-degree angle you focus on, but for the purposes of teaching, let's focus on this 45-degree angle, which makes this opposite, this adjacent. Root 2 is still my hypotenuse. So when I do the sine of 45, which is opposite over hypotenuse, I get 1 over root 2. The cosine is adjacent over hypotenuse, which is 1 over root 2. And the tangent is opposite over adjacent, which is 1 over 1. When I rationalize, the sine of 45 degrees is root 2 over 2. The cosine of 45 degrees is also root 2 over 2. And the tangent is 1. Just to prove to you that it didn't make a difference if I picked 1 or whatever number, let me pick a different number. All right, if this is come on, let's erase. If this is an isosceles right triangle, let me make up a number. Let's make this 7, all right? Then this side has to be 7 because by definition of isosceles, your sides opposite them have to be the same. Then if I do Pythagorean theorem, again, I know some of you will hopefully remember your special right triangles. I get 49 plus 49 equals c squared. I'm going to take a square root of this. So isn't 49 plus 49 also 49 times 2? So I get 7 root 2 is c. All right, and notice that if I do the sine of 45, so if this is still my opposite, this is still my adjacent, this is still my hypotenuse, then I would get 7 over 7 root 2, which reduces to 1 over root 2, which gives me root 2 over 2. If I would do 7 over 7 root 2, I still get root 2 over 2, and my opposite over adjacent still yields 1. So our last slide for today is let's talk about finding the sine, cosine, and tangent of 30 and 60-degree angles. And again, we are referring to that special right triangle business. What I have up here is an equilateral triangle because I have all 3 sides congruent. If it is equilateral, it's also equiangular, which means every single angle is 60 degrees. Yep, the flashbacks are coming back. Now, I'm going to be strategic, and I'm not going to do 40 million examples, but just like in the previous problem where I just picked an arbitrary number to be the length, I'm going to let each side of this equilateral triangle be 2. Here's what I'm going to do now. I'm going to make a right triangle by dropping down a perpendicular bisector. Okay. And when I drop that perpendicular bisector, I bisected this angle. So that means I have a 30-degree angle up here, I have a 60-degree angle here, and I have a 90-degree angle. For the moment, I would really like to just focus on this right-hand triangle. Okay. If this side over here, if this side right here is 2, because and that was an arbitrary number I picked, then this side right here would have to be, since I did a perpendicular bisector, I cut it in half, this side would have to be 1. Then if I want to figure out this side, I can do by Pythagorean theorem. A squared plus 1 squared equals 2 squared. So a squared plus 1 equals 4. A squared is equal to 3. So a is root 3. Again, I'm not worrying about plus or minuses as I do Pythagorean theorem because we're talking about distances and distances can't be negative. So let me draw this a little bit prettier for you to see. Let me get a 30, 60, 90 triangle. All right, and let me flip it left, right, and then here. All right, so hopefully I've rotated that. All I'm trying to do is take this triangle and I'm just going to write it over here a little bit prettier. This was my 30-degree angle. This was my 60-degree angle. This was 1. This was 2. So your short side, which is opposite to 60, is half the hypotenuse. And when I do Pythagorean theorem, then the long side is your short side times root 3. So again, we're going to be doing more review of those special right triangles. So if you're like, oh, I don't know if I remember all that, trust me, you'll know it by the next lesson. Okay, so if I do the sine of 30, I'm focusing on my acute angle 30, which means the 1 is an opposite leg, root 3 is adjacent, and 2 is my hypotenuse. So the sine of 30, if I do SOH-CAH-TOA, okay, is opposite, which is 1, over 2. My cosine is the adjacent, which is root 3 over the hypotenuse of 2. And my tangent is going to be opposite, which is 1 over root 3. I don't have to rationalize the cosine, right? But I do need to rationalize the tangent. So I get root 3 over 3. All right, now let's focus in on the 60. Okay, so if I focus in on the 60, now the root 3 is opposite. The 1 is adjacent. 2 remains my hypotenuse. So if I do opposite over hypotenuse of 60, I'm going to get root 3 over 2. If I do the cosine, which is adjacent over hypotenuse, then I'm going to have 1 over 2. And the tangent of 60 is going to be opposite over adjacent, which is root 3 over 1, or just root 3. No rationalizing necessary. Thank you for listening, and we will pick up the rest of this lesson in class. Look forward to seeing you then.